All right, we're moving into indeterminate trusses, also using the force and flexibility method. So hopefully this shouldn't be too long because I'm just going to talk about it for a second and then do an example. By the end, you should be able to determine the reactions and member forces for an indeterminate truss using the force and flexibility method. So let's recall back in lecture 4, I believe, where we talked about statically indeterminate trusses and how to determine if it was indeterminate or not. And we have our unknowns for a truss, which are our reactions at our supports and our member forces or our bar forces. What do we know? We have equations of equilibrium, right? We can solve the sum of the forces in the x and the sum of the forces in the y that equals 0 at each joint. So on the unknowns, I have R plus B, and on the knowns, I have two equations of equilibrium per joint, so 2J right? If R plus B, if my reactions plus my member forces is equal to 2 times J, then I'm statically determinate. If R plus B is greater than 2J, I have too many unknowns, then I'm statically indeterminate. Well, the trusses. I'm pretty determinate, I guess. And I can subtract how indeterminate is my truss. R plus B minus 2J is my degree of indeterminacy. So what I'm going to do is I'm going to do an example and then I'm going to summarize the procedure because it's better to do it and then go back and say, okay, what did we do? It's a little bit easier to explain than doing it the opposite way. So let's look at this truss here, and we want to find the force and member AC is the goal. So let's see. How many reactions do I have? Right, my reactions. Let's see. I've got a horizontal reaction at E and a vertical reaction at E. And I've also got a horizontal reaction at D and a vertical reaction at D. So my number of reactions, 4. 1, 2, 3, 4. my number of bars or members. Now we're assuming that these are not attached. They're not, it's not a joint, they're just overlapping. So my number of bars, I've got 1, 2, 3, 4, 5, 6, 7. And my number of joints, 1, 2, 3, 4, 5. So R plus B is 4 plus 7. That's 11. That's my number of unknowns. My number of knowns is 2J, which is 10. So I've got a statically indeterminate truss, right? And how indeterminate is it? 11 minus 10 is 1. So 1 degree indeterminate. So that means I need 1 redundant structure. How do I do that? I am going to cut one of my bars so it has no force in it. So I have to determine the force in AC, so I'm going to cut it. And I mean, I'm going to, right? I'm going to get rid of all this. So I'm going to cut member AC. Now, AC might be free to pull apart, right? If I apply my loads, there's nothing keeping that together. So there's going to be some type of displacement. And that's going to be my primary structure. And then my virtual structure and then my redundant structure, not my virtual. My redundant structure I'm going to apply some load, FAC, to close that gap. And that gap is calculated using a flexibility coefficient. So my compatibility equation, right, let's say apply FAC to close that displacement. And that which we've calculated before as like a delta prime, right? So member in AC, force of member AC due to a unit force at AC, right? And before we know that we can calculate that using a flexibility coefficient, right? Little script F. So my compatibility equation, because I don't want there to be a gap, is the gap if that member has no force in it, plus the gap that closes it, which is equal to 0. So I'm going to cut that member and allow it to have an opening, because it's not, you know, it's not a force holding that thing together. So if I cut it, maybe it moves apart, right? Yeah. Let's see. Right? Maybe it moves apart. And I'm going to find the force required to close that gap. Okay, this might make more sense as we start doing it. All right, this is a delta AC due to member being cut. So here I have my primary structure, and I cut it. And I cut it, meaning there's some gap, right? How do I find out what that deflection is? I'm going to do a virtual load of 1 to find that deflection. So this My primary structure now gets broken up into a real structure and a virtual structure. If I cut it, there's a displacement, and maybe an elongation or a compression. And I'm going to apply a unit load in that member to find that deflection. Right? So I need to break this up into 2 more structures. The good news is this is useful in a minute. So I'm going to look at my real structure where I have, and I'm going to eventually fill out, right, this little table that we talked about doing virtual work. So here's my real structure. I've cut member AC, so it has 0 forces in it. Right off the bat, I can figure out that I have some other 0 force members. If you look at joint C, now that there's no horizontal component for member AC, and there's only the load in the vertical direction, BC has to be equal to 0. If you look at joint B, there's no horizontal component from BC, so BD has to be 0. Are those all my 0 force members? Yeah. Now remember, when we're solving trusses, you can do method of joints or method of sections. And you can at most have 2 unknowns per joint or 3 unknowns per section. So I'm actually just going to do the method of joints. Actually, first of all, I'm going to, right. If I look at joint B, that's pretty easy. I'm just going to draw it for posterity, but, right? It's got 6 kip load, 0, 0. So the only thing I have is AB. So FAB equals, right? It's in tension. If I go look at joint D, not joint D, joint C, I'm going to find a similar story, right? It's got 6 kips, but 0 in member BC, 0 in AC. So it's got force CD equals plus 6 kips and tension. If I go over to joint A, let's see. I have two unknowns. I don't know AD and I don't know AE, but that's fine. That's the most that I can have. Let's see, I've got the 6 kips tension in AB. I've got nothing in AC. And then I have force in member AE and force in member AD. So if I do the sum of the forces in the X direction, or I'm sorry, in the Y direction, right? FAE, right, if I go like this. I know that the Y component of FAE is going to be up 6 kips, right? And thank goodness I've got a 3, 4, 5 triangle, right? So this is 8, this is 6, this is 10. So FAE is 6 kips times what? 10 feet over 6 feet. So it's 10 kips. And it's going to be going this direction, so it's tension. So it's positive. Right. So this is plus 10 kips. If this is 6 and this is 10, then this is 8 kips, the horizontal component. So if I do sum of the forces in the X direction, the only one I have is FAD. It's got to be going to the left because that 8 kips from FAE is going to the right. So it's 8 kips, and I'm going to put negative because it's going to the left. So it's in compression. It's compressing AD, right? So this is negative 8 kips. So now I have all of my member forces, right? 1, 2, 3, 4, 5, 6, 7. All right. See, that wasn't that hard. It helps when stuff gets 0 right away. So that's my real structure for my primary structure. All right. We're like sub of a sub here. So now I need to look at my, virtual structure. What I'm going to do is I'm going to close that gap by adding a virtual load, which basically makes so that makes member AC, I'm going to assume it's in tension, so it's going to be a +1. Now you can do the same thing looking at the method of joints and figure out, or method of sections, however you'd like to do it, to figure out the forces in your members. So I'm going to give you guys about 5 minutes. See if you can come up with them on your own. Oops. Come back. There it is. Okay, it's been about 5 minutes. Yeah. So if you haven't done it, pause if you want to keep going. But, right, let's look at I'd start down here at joint C because I have two unknown member forces, BC and CD. Right, if this is 1, then BC and FCD, right? They're going to just be the horizontal and vertical components of that 1. So let's see, 1, 3, 4, 5 triangle. So 8 is at the bottom, so this is 0.8, and this should be 0.6. So FCD is negative 0.6, right? It's in compression. And BC, negative 0.8. Go look at A, or B, I'm sorry. Let's see. I've got that 0.8 from BC. It's in compression, so it's acting that way. Then I have FBD and FAB. BD is just going to be, if you haven't figured it out, it's probably 1 because, right, it's got to be 0.8. Right? So that's 1, that is 0.6. So BD is plus 1. That means FAB is going down because it's going to be the vertical component of BD. FAB equals negative 0.6. If I go over to joint A, let's see, I've got 1 acting tension, 0.6 acting up. See, that means this has a component of 0.6 and 0.8. So that's going to be 0.8. What does that mean for AE? It's a 0 force member, because if I do the sum of the forces in the X direction, actually, yeah, right, let's draw that a little bit better, right, 0.6, 0.8. So if I do the sum of the forces in the Y direction, that means there can't be any force in AE. So FAD has to be the 0.8 in the opposite direction. Should have probably done that one first. But yeah, so that's 0. By not doing it first, I was ignoring it. So FAE is 0. FAD equals negative 0.8. So now I have all the forces in my real structure and all the forces in my virtual structure. So I get to go back to my little table. Right? This is for my forces in my virtual, which is that baby N. This is for my forces in my real, which is big N. So let's look at my members. Look at it while you can, right? I have members AE, AD, AC, B, if I go and look at my virtual, right? This is from my virtual load. I've got 0, negative 0.8, plus 1, negative 0.6, plus 1, negative 0.8, negative 0.6. If I go to my real structure, plus 10 kips, let me write that a little better, plus 10 kips, minus 8 kips, 0, plus 6 kips, 0, 0, plus 6 kips. If I look at my lengths, AE is the square root of 8 squared plus 6 squared, so that's 10 feet. AD is an 8-foot horizontal member. AC is 10 feet. 6 feet, 10 feet, 8 feet, and 6 feet. It said in the problem statement that AE is constant. So, spoiler, they're probably gonna come out, so it doesn't matter. So right away, I'm just gonna write, this one's gonna be 0, this one's gonna be 0, 0, 0. So I need to sum, or I need to multiply little n times big N times L over AE, right? So negative 0.8 times negative 8 times 8 is 51.2 kip feet per AE, right? Negative 0.6 times 6 times 6, negative 21.6 kip feet per AE. Need to make that column bigger, huh? And then negative 0.6 times plus 6 times plus 6 is again negative 21.6 kip feet per AE. If I add those up, I get 51.2 minus 21.6 minus 21.6. 8 kip feet per AE. So what was I doing all along? I was trying to figure out the deflection in member AC if it was cut, if there was zero force in it. So I know it's 8 kip feet per AE. If I wanted to find that actual number, I'd need to assume an A and an E. They should be dropping out though. So that is for my primary structure. Now I get to do the same thing for my redundant structure. My redundant structure means that I've cut this and I'm applying some load. Oops. And I'm applying some load in AC. So it's a virtual load 1 times FAC. So I can apply a unit load and then calculate that deflection. Well, and that gives me my flexibility. My flexibility of member AC due to a unit load in AC. Due to a load in AC, right? Well, didn't I just do that as my virtual load? Yay. I already did all this. I don't have to do it again. So, what I'm going to go do is steal the answers from the primary load, from the primary structure, right? Look, I'm super lazy, and I just did that. Right? Look at that. And I get so I get to do it another time too, right? Oops. Hey, I'll just keep it like that. Right? 0, negative 0.8 plus 1 minus 0.6 plus 1 minus 0.8 minus 0.6. My same lengths, 10 feet, 8 feet, kind of goes along with the numbers, doesn't it? So only the top one's going to be 0 this time. But I get to multiply my two virtual loads. So basically I'm squaring my virtual loads and multiplying them by the length. 5.12 feet per AE. 10 feet per AE. Start to notice a pattern compared to the last one, right? These are the same numbers, similar numbers. And 2.16. If I add all those together, 34.56 feet per AE. So my flexibility is 34.56 feet per AE. Right? Kind of weird that there's no force component, there's no force unit in there, because the force unit is going to be in that E, right? If I could make feet, and let's say the area is feet squared, and my elastic modulus is kip per feet squared, right? Now my units are foot per kip, and I'm going to calculate that. Which is what I want it to be, because I'm going to multiply that by a force, and I want to get a displacement unit, so feet, inches, what have you. So I did all that. That was super easy, right? Go back to my compatibility. Right, my deflection in AC, if it's cut, plus my flexibility in AC due to that unit load in AC times the force in AC if I, the force to close that gap, right, is going to be equal to 0. That means my FAC is equal to negative delta AC divided by that flexibility component. So if I go back and look, my deflection in AC, probably going too fast. My deflection in AC, oh, it's all the way back at the beginning. There it is. 8 kip feet per AE. Negative 8 kip feet per AE. My flexibility component is 34.56 feet per AE, so I'm going to do 34.56. Voila, those go away. So I find my force and member AC is -8 divided by 34.56. I get 0.231, and that's kips because look, my feet go away, which means it's in compression, right? FAC is 0.231 kips. It's in compression. And there is your answer. So let's take a moment and summarize this, what we just did, right? First, and I'm following similarly to what we wrote for beams, right? Determine your number of redundant, like if you're statically indeterminate, your degree of indeterminacy, which means how many redundant structures you write, right? Determine right. My unknowns are my reactions and my bar joists. My knowns were my two equations of equilibrium per joint. So R plus B minus 2J is my degree of indeterminacy. And the number of redundant structures. So I'm going to draw, my next step is to draw my primary and redundant structures. Right, this is my, I'm going to remove redundant bar forces, member forces, and then I'm going to apply them in my redundant. Again, my primary first of all, I should probably check, but they're statically determinate and the same. The primary has the actual loads on it from your real structure. The redundant the only, you assume a member force for the members that you've removed as redundant. So let's see. I'm going to write my compatibility equation. This would be sum of your deflections is equal to a known quantity. Maybe it's 0. Maybe you're like, what are the forces in my members if I allow member AB to elongate 0.5 millimeter? No, you know. So it might be 0, but it might be something else. And then I'm going to use virtual work. To determine my deflections in primary structure. This would be, right, deflection is the sum of the virtual loads, the real loads, the length over AE. And then I get to use those virtual loads, right? Flexibility coefficient and redundant structure. Right? Now my flexibility is equal to the sum of my virtual loads, basically squared over A. From there, I get to calculate my redundant bar forces, right? Force, well, yeah, it's based on your compatibility equation. And if you need to, use equilibrium to find your remaining bar forces and reaction. And that's it. Right? So we did an example of that already. I just wanted to do the example before we did the summary of the procedure. And now you can use the force method to solve trusses, statically indeterminate trusses. And that is all that we are going to do for indeterminate structures. Okay? Let me know if you have any more questions, and have a good day. Maybe.